video is going to review the topic of stoichiometry, which is how we study the quantitative relationships between reactants and products in a chemical reaction. So this will be very closely tied to the last section on balancing equations, because we're going to use those balanced equations to decide things like how many particles of product can we make if we have a certain amount of reactant, or how much reactant do we need if we want to make a specific amount of product. So to give an example, what I'm going to do is start out by saying, let's consider the reaction between carbon, C, plus hydrogen gas, H2, to make CH4, which is methane. So in the balanced equation, there will be 2 H2s for every 1 carbon. So there's a 1-to-2 ratio. And what makes stoichiometry a bit different from just regular balanced equations is that the balanced equation considers the bare minimum number of particles that need to react with each other in terms of integer numbers, so 1 carbon and 2 H2 particles. However, in the lab, you're almost never going to have precisely 1 particle and 2 particles reacting. Molecules are so tiny that even saying millions wouldn't be enough. We're going to have an accountable number of molecules reacting, but it's so huge that we might as well just be thinking about things in terms of ratios. So the 1-to-2 ratio of carbon to H2 is what's really important here. So let's say that instead of considering a 1 particle of carbon to 2 particles of hydrogen, let's say we have 2 particles of carbon and 4 particles of hydrogen. So they're just interacting with each other. Those are going to react to make CH4. So the 1-to-2 ratio means every time we have a single carbon, it needs 2 hydrogens to react with. So we can kind of group this one with those 2. So that's 1 reaction of carbon with H2. And this is another one. So the reaction can happen twice with 2 different carbon molecules. Since it happens twice, we're going to end up with 2 CH4 molecules as our product. So instead of just doing the reaction once, we're doing it twice. And this could scale up as far as you want it. So if you had 1 million particles of carbon, you would need 2 million particles of hydrogen gas in order to make the reaction make 1 million particles of methane. But this ratio will not always be perfect. So let's get rid of these. Let's consider that our ratio is, instead of being 1-to-2, let's say we have 1 carbon particle and we still have 4 H2 particles. Okay, so 1 carbon can still only react with 2 H2 particles. So let's say it reacts with these 2. That can give us 1 equivalent of CH4. But those other 2 hydrogens are not reacting. They're just sticking along behind, staying as H2. They're not getting converted. That makes them excess reactant. And what that tells us is that we can call carbon something called the limiting reagent. So the limiting reagent is whatever gets consumed first. So all of the carbon gets consumed, but then there's leftover hydrogen. So the concept of the limiting reagent will be very important for you when you start doing calculations to determine how much of your reactants do you need to make a certain amount of product, and which one is in excess and which one is limiting. And this could work the other way around. So for example, carbon doesn't have to be the limiting reagent. It just is in this case. So let's see what it looks like for hydrogen to be the limiting reagent instead. So let's say we have 3 particles of carbon and 2 particles of hydrogen. Well, this carbon could react with 2 hydrogens, but then we would have 2 carbons left over. So we still end up making just 1 equivalent of CH4 here. But this time, the carbon is the excess reagent and the hydrogen is the limiting reagent. So the last thing I want to cover in this video is the opposite type of prediction. So for example, let's say we're told how much CH4 we need to make, and then based off of that, determine how much of our reactants we need. So let's say that the question tells us we want to make 3 CH4 particles, and it says, how many particles of H2 do we need to make this happen? Well, what we can do is look at the balanced equation. We know that every time we have 1 CH4, we need 2 H2 particles. So that means that if we want to know how much H2, well, what we can do is we can say that if we have 3 CH4, we know that there is a ratio of 2 H2 for every 1 CH4. So the way that I set this up was so that the CH4s would cancel out with each other. And in this equation, it leaves us with H2 as the only thing left over, which is what we're trying to solve for. So this would be 3 times 2. We would need 6 H2 particles to make that happen. And you can set up a similar equation for carbon. So for carbon, we could say, well, if we have 3 CH4 particles, we know there's a ratio of 1 carbon for every 1 CH4. So the CH4 and the CH4 cancel, leaving us with just carbon left over. So 3 times 1 is just 3. So we would need 3 carbon particles to make that happen. So that's the basics of stoichiometry. You can apply this to any balanced equation. In the next video about stoichiometry, what I'm going to cover is how we're going to look at this in terms of mass instead of just looking at it in terms of particles.